Hello my friends, this is Unit 1, Lesson 2, Law of Levers. Law of levers, it's a mathematical equation that explains the relation between effort force and resistance force. So this is a mathematical equation and it explains the relation between the effort force and the resistance force. We have learned from the previous lesson that the lever is a rigid bar. It rotates around a fixed point called fulcrum and is affected by effort force and resistance force. Look at this crowbar. This is a rigid bar. It has a fulcrum. It has a resistance force and it has effort force. Law of levers. It states that effort force times its arm equals resistance force times its arm. Effort force times its arm equals resistance force times its arm. Law of levers. Effort arm and resistance arm. Effort arm is the distance between effort and fulcrum. This is called effort arm. It's the distance between the effort force and the fulcrum, while the resistance arm is the distance between the resistance and fulcrum. So this is the resistance arm. It's the distance between resistance and fulcrum. And this is the effort force arm because it's the distance between the effort force and fulcrum. The measuring units of effort force and resistance force is Newton, while the measuring unit of effort arm and resistance arm is centimeter or meter because the arm is a distance. In the first class levers, when the force arm equals to resistance arm, so this means that the effort force equals to resistance force. My effort is similar to the resistance, so this means that this lever doesn't conserve effort or has no mechanical benefit. As you can observe, my friends, here the force arm equals to resistance arm. So this means that resistance is equal to the force. So this lever doesn't conserve effort. The second case in the first class levers is that when the force arm is longer than resistance arm. When the force arm is longer than resistance arm, so the opposite. My effort is smaller than resistance. So this lever conserves effort and has a mechanical benefit. You can observe here, my friends, that the effort force arm is longer than the resistance arm. So when the force arm is longer, so the effort force is smaller than resistance force. So in this case, the lever conserves effort. Why? Because the effort I exert is smaller than the resistance, so it saves my effort. In this case, the lever conserves effort and has mechanical benefit. In the third case, in the first class levers, when the force arm is shorter than resistance arm. Can you see here? This is the effort force and this is the fulcrum. Look at the distance. This is a very small distance. The force arm is shorter than the resistance arm, and so the opposite, my friends. When the force arm is small, the effort will be bigger than the resistance force. So in this case, this lever doesn't conserve effort. So my friends, in the first class levers there are three possibilities. When the force arm is shorter than the resistance arm, so the opposite. The force arm is shorter, so the effort force is larger than resistance. So my effort is very big. Does this lever save effort? No, it doesn't save my effort because the force is larger than resistance. And in the second case, when the force arm is equal to the resistance arm, this means that force equals resistance, so it doesn't conserve effort. My force is equal to resistance. It doesn't save my effort. But when the force arm is longer than resistance arm, as in this case, force arm is longer than resistance arm, so the effort force is smaller than resistance force, so the first class lever in this possibility conserves effort. Let's transfer to the second class levers. Force arm is always longer than resistance arm, so the opposite. Effort force is always smaller than resistance force. So in this case, the lever conserves effort. Second class levers always conserve effort. Look here, my friends. In second class levers, the resistance is always in between the effort force and fulcrum. Where is the force arm? All this. The distance between force and fulcrum is called force arm. And where is the resistance arm? This. The distance between resistance and fulcrum. So, always the effort force arm is longer than resistance arm. So, when the force arm is longer, so the force is small than resistance. I exert a small effort. So, my friends, this lever conserves effort, always conserves effort and has mechanical benefit. Why? Because the force arm is always longer than resistance arm. So the force is smaller than the resistance. Give reason, nutcracker and wheelbarrow save effort or have mechanical benefit. Why wheelbarrow and nutcracker have mechanical benefit? These levers are from the second class levers. So the answer will be because force arm is always longer than resistance arm, so the opposite. Force arm is longer, so the effort force is smaller than resistance. It saves my effort. I exert a small effort, so it saves my effort. It has a mechanical benefit. In the third class levers, force arm is always shorter than resistance arm. So the effort force is always greater than resistance force. So these levers always don't conserve effort and has no mechanical benefit. Look at this. My friends, this is a third class lever. The force is here and resistance is here and fulcrum is here. Where is the force arm? Here it is. This is the force arm. And where is the resistance arm? All this distance is the resistance arm. The distance between resistance and fulcrum is called resistance arm, and the distance between force and fulcrum is called force arm. So the force arm is smaller than resistance arm, so the force is bigger than resistance, so this lever doesn't conserve effort. This is, my friend, is a fishing hook. In the fishing hook, as you can observe, the resistance arm is longer than the force arm. So when the force arm is short, this means that the effort force is bigger than the resistance, and in this case, this lever doesn't save effort, but it helps the fisherman to catch the fish. All the third class levers And some of the first class levers that don't save effort are beneficial in other things, as they increase the distance, increasing speed, avoiding dangers, accuracy in performance. So they are important. They don't save effort, but they are important. They increase the distance, increase the speed, avoid dangers, and accurate in performance. Remember, law of levers states that force times its arm equals resistance times its arm. Let's solve this problem, junior 6. In a second class lever, the effort force is 100 Newton. The length of the force arm equals 25 centimeter. The resistance equals 500 Newton. Calculate the resistance arm. In order to solve this problem, my friends, you have to write the law of levers. Law of levers states that force times its arm equals resistance times its arm. Force equals 100 Newton. The force arm 25 centimeter, so we write 25. The resistance equals 500 Newton, so we write 500. And the resistance arm is unknown. So resistance arm equals 100 times 25 divided by 500. The result will be 5 centimeter, and you should write the unit centimeter because it's a distance. Resistance arm here equals 5 centimeter. In a third class lever, the effort force is 200 Newton and the length of the force arm equals 5 centimeter. The resistance equals 100 Newton. Calculate the resistance arm. In this lever, we have the effort force, the force arm, and the resistance, and the resistance arm is unknown. In order to solve this problem, you should write the law of levers. Force times its arm equals resistance times its arm. Then write the given numbers. 200 times 5 equals 100 times resistance arm. The resistance arm equals 200 times 5 divided by 100, and the result will be 10 centimeter. Don't forget to write the unit. Don't forget to write the law of levers. Let's solve another problem. An effort force of 500 Newton affects a first class lever, and its arm of force arm equals 10 centimeter. So the effort force equals 500, the force arm equals 10 centimeter, resistance equals 200 Newton, and the arm of resistance equals 20 centimeter. In this example, is the lever in a state of balance or not, and why? Force is given, force arm is given, the resistance is given, and the resistance arm is given. The problem wants you to say, is this lever in a state of balance or not? So we will answer as follow. Force times its arm equals 500 times 10 equals 5,000. Resistance times its arm equals 200 times 20 equals 4,000. And the law of levers states that force times its arm equals resistance times its arm. Does 5,000 equal 4,000? No. So in this case, in this lever, force times its arm is not equal resistance times its arm. So my friends, this lever is not in a state of balance. Give reason? Because force times its arm is not equal resistance times its arm. This is all about our lesson for today, and study hard and goodbye.